Hi everyone, welcome back. In this video we're going to continue our investigation of using algebra to solve kinematics problems, and in this situation we're going to investigate how to deal with situations where there are two objects racing against each other. So when that's the case, what we're often interested in is how long does it take for one object to catch up to another, and how far do one or both objects go during this time of catching up. So let's just go through this with a detailed example. Consider two cars side by side, a red car and a yellow car. A red car is traveling at constant velocity at 15 meters per second, and at the instant that the cars are side by side, the yellow car accelerates at 3 meters per square second from rest. How much time passes before the cars are side by side again? Now this might be kind of similar to a situation in traffic where somebody is driving and they have a stoplight perfectly timed, and they realize that they don't need to slow down because they know that it's they have it perfectly timed, and it's a very risky behavior. I do not recommend engaging in this, but in any case, at the instant that the light turns green, the person who has it perfectly timed ends up zooming by the person who's at a stop in the next lane. And at that instant, that person ends up hitting the gas, and the question is, how long does it take for the person who was at rest to catch up to the person who zoomed through if the person who had been at rest is accelerating at a constant rate? So, in this case, we have two sets of givens, one for the yellow car and one for the red car. When you're actually writing these down on your own paper, where you can't use colors and stuff like that very easily, I would recommend using subscripts. So for example, you would say v0, comma y for v0, comma yellow, or for the initial velocity of the yellow car is 0. And a sub y is 3 meters per square second, the yellow car's acceleration. v0, comma r, in other words, the 0 and r are both in the subscript. v0, comma r, the initial velocity of the red car is 15 meters per second, and its acceleration is 0, so a sub r would be 0. So that's how I would recommend notating this if you don't have colors with you and stuff like that. And even if you do, I would recommend using subscripts. But here, just to illustrate the process in the PowerPoint, we're going to avoid that and just use shading colors. Well, what equation are we going to use? The whole point is that there is a point in time when the cars are right next to each other again. We are assuming that there is some point in time when the cars are right next to each other. Question is, what is that time? So, what does it mean to be right next to each other? In other words, what does it mean to catch up to the other person? It means that your position, your final position, is equal. So in this case, instead of saying delta x equals v naught t plus a half at squared, we're actually going to write the equation out as x equals x naught plus v naught t plus 1/2 at squared. In other words, that delta x is x minus x naught, and we move the x naught to the right side. The reason we're doing that is because there might be problems where, say, maybe the yellow car doesn't start accelerating until after the red car is maybe 3 or 4 or some number of meters in front of the yellow car. And in that case, the red car and the yellow car would have different values for their initial positions, but we still want to solve it so that they have the same values for their final positions. In this problem, their initial positions, x naught yellow and x naught red, are the same. So it turns out that we'll just call them 0, and even if we didn't call them 0, they would cancel. So for the red car, that part's easy because the red car's acceleration is 0, so no 1/2 at squared term. For the yellow car, that part's also a little easy because its initial velocity was 0, so no v naught t term. And again, the x naughts cancel, and we're just going to be a little sloppy and call them both 0, but in any case, they cancel. The point is, we set x red equal to x yellow. In other words, there is some time, we are assuming that there is some time when their final positions are the same. If it turns out that there is no such time, then when we solve the equation, we're going to get imaginary numbers for time, which would mean that our assumption that they had the same position at any point was wrong. So, anyway, just in this case, eschewing the units, because we've already written them out here, just showing the method, we say, okay, well, x red is equal to x yellow, so the final red expression for x is equal to the final yellow expression for x. Sorry, the red is on the right, yellow is on the left. So we switched that a little bit here. But now what we're going to do is we're going to move all the terms to one side of the equation. You might wonder, is like, well, can't we just cancel a t? Well, you might think so, but by canceling, what are you actually doing? You're dividing both sides by t. But generally speaking, it's not a good idea to divide both sides by a variable. At least when you do, you have to be very careful to make sure that that variable can't be equal to 0, because only Chuck Norris is allowed to divide by 0. So instead what we do is we move all of our terms to the right side of the equation, and we realize that we can factor out a t. We have a product of two things equaling 0. Well, the only time the product of two things can be equal to 0 is if one or both of them is equal to 0. So one solution will be that the first one is equal to 0. The other solution will be that the second term is equal to 0. Well, if the first term is equal to 0, that's just t is equal to 0. If the second term is equal to 0, that would be 1.5 t, that is 1.5 meters per square second t minus 15 meters per second is equal to 0. And that would lead to t being 10 seconds. So just showing the whole math, I mean, you set the distances equal to each other. The distance equations are now equal to each other. In other words, we plug in the equations, have the t's on the same side, factor it out, and then you get two possible solutions. One of those is a trivial solution. In other words, we already knew that the cars were right next to each other at time 0. So that doesn't tell us anything new. But we do also learn that the cars are again right next to each other after 10 seconds. So in terms of trying to get full credit, well, you would have two lists of givens. You would have your variables, numbers with units in your givens, and then showing the plugging in of your numbers with units into the equations. And showing the math steps, and then your final answer with units. So just a summary of this type of problem for the racing situation. You make two lists of givens, and given the problem, you're going to need to look for each object's acceleration and initial velocity. Sometimes that will be obvious, sometimes you'll have to read into the problem a little bit to figure it out. Keep in mind that constant velocity means 0 acceleration. That will sometimes occur in for at least one of the objects. And you're always going to use the same formula. That is where the whole point is that their final positions are equal, and you're going to solve for the time when the final positions are equal by setting the x's equal to each other. X for one is equal to x for the other, and then you plug in the givens and isolate for the time. In terms of the math, well, two cars are covering the same distance in time, so their x's are equal, and then you set their distance equations equal. We put the t's on the same side. We simplified, we pulled out a factor of t, and you realized, okay, either t is equal to 0 or 1.5t minus 15 is equal to 0. And remember, you can't divide by a variable. If you do, you'll lose points because, after all, it could turn out that the variable is equal to 0. If you know that it's not equal to 0, it's actually okay to do that. But in this case, it turns out it is equal to 0 in one situation. So you can't do that. But in any case, the non-trivial solution that you get is t is 10 seconds. And yeah, make sure that when you're actually solving the problem, you plug in your units. Here we eschewed those just to show the main method. Let's look at another example. In this example, consider an attack helicopter flying at 108 meters per second relative to the ground, and a jet fighter zips by at 378 meters per second. So at the instant the jet flies past, the helicopter fires a missile that accelerates at 2.25 Gs. Calculate how long it takes for the missile to catch the jet, and how far the jet travels before the missile catches it if the jet maintains constant speed and direction throughout the problem. So again, we write our givens. Here we're going to use subscripts. So I'm going to use J for jet and M for missile. So the initial velocity of the jet is 378 meters per second. Its acceleration is 0, which means its final velocity is the same as its initial velocity. Because after all, if the acceleration is 0, that means the velocity doesn't change. The initial velocity for the missile is 108 meters per second, but it does have non-zero acceleration of 2.25 Gs. But wait a second, Gs are not SI units, so we need to plug in the fact that G is 9.80 meters per square second, so 2.25 times 9.80 is 22.05. So there's the missile's acceleration in SI units of 22.05 meters per square second. So Here, the initial positions of the jet and the missile are the same. So we note that. And also, keep in mind, the missile catches the jet, which means their final positions are the same. What does that mean? Well, I have an equation for x, coming from the delta x equation and having rearranged to put initial position on the right side. But in any case, we have the x naught for the jet plus v naught jet t plus a half a sub jet t squared is going to be equal to x naught for the missile plus v naught missile t plus a half a missile t squared. So that's what we're going to have as our next step. So here's where we're at so far, and now we set the equations equal to each other. So there we go. And now, first of all, the initial positions were the same, so we can cancel those. The acceleration of the jet was 0, so that term simply disappears. The initial velocity of the missile this time, though, is not 0, so v naught missile t does not disappear. In this case, we have initial velocities for both of the objects that are not 0. So again, we move everything to one side of the equation. We don't have to use a quadratic formula here or anything. We would potentially have to use a quadratic formula, though, if they did not start at the same spot, so beware. But in this case, they start at the same spot, so we can just factor out a t. So we've factored out a t. So this means that either t is 0 or the thing in parentheses is 0. So, well, the t equals 0 solution, that's the trivial solution. We already knew that. We already knew that the jet and the missile started off at the same position. But the question is, what happens when the thing in parentheses is equal to 0? So that's the solution we care about. So I decided to move my term that had t over to the other side of the equation, keep everything that didn't have t on the right side of the equation, and then I flipped the equation. And then from here, multiply both sides by 2, divide both sides by the acceleration of the missile. So now we have been good physics students. We have solved for the unknown in terms of our givens. Now we're ready to plug in numbers. This case was a situation where it actually is easier to solve for the unknown first before plugging in numbers, because a letter doesn't take anywhere near as long to write as a number, with units and all of that sort of stuff. So now, finally, at the very end, we plug in our numbers with units. We notice that the meters cancel, and we have 1 over seconds in the numerator, 1 over seconds squared in the denominator. That becomes seconds squared over seconds, and that just leaves us with seconds for our units, which works out because, after all, we're looking for a time. And that time turns out to be 22.5 seconds, is how long it takes for the missile to catch back up to the jet and possibly destroy it. So, how about calculating how far the jet traveled before being hit by the missile? Well, what we need to do is we need to use the equation for the displacement of the jet. Well, delta x for the jet is v naught jet t plus a half a jet t squared. But remember, the acceleration of the jet was 0. So apparently the pilot stupidly did not make any maneuvers of any sort to try to confound the missile. So what we're left with is just the initial velocity of the jet times the time it took for the missile to catch up to it, which we have from the previous part. And that turns into, multiplying them together, a distance of 9,260 meters, so about 9.26 kilometers. So I guess that's a little shy of 6 miles. So in the next type of problem, we're going to look at situations where the acceleration ends up changing. And that's a completely different type of scenario, which we will look at in the next video. So I'll see you all then.